So, welcome to power system classes. Like we were actually looking at, hope you are actually listening because, okay. So I hope you are like it's audible. The last class we were looking at the what is known as the load flow studies. So basically, I have said that the load flow study is for finding the voltage and the angle of the voltage and the magnitude of the voltage and power at each buses. Okay, so what are the important methods by which actually we can find the load flow studies? So the first one is basically known as the Gauss-Seidel method. Gauss-Seidel method, or actually I have explained in the last class how to do that. Okay. Gauss-Seidel iteration method. Okay, so we have looked at that. So what is the the most important equation in this one is like any V2. Actually, I am taking the second class is equal to 1 by y22 into P2 minus JQ2 divided by P2 star minus y21 V1 plus y23 V3 etc. up to y2n Vn. Okay. So we already know what is the scheduled power in actually P2 and Q2 if it is a load bus, and if it is not a load bus, we have to find the P2 and Q2 there, and we actually put an initial guess for V2. So using all, because these we know, we actually put some initial values for we take an initial bus voltage matrix V1, V2, etc. up to Vn. Like we can take first as 1 angle 0 and others like you can take an initial guess. And using this initial guess, we will actually iterate. Okay. So with all these, V1 to Vn, we actually iterate and find the new value of V2. So using the new value of V2, then we will find the new value of V3. So like that, we have to actually update the equation. Like so, after some time, what happens is that V2n plus 1 minus V2n. If you take the magnitude of this will be less than some epsilon. Epsilon is a very, very small number. That means the next iteration will be same as the previous iteration. Okay. So that means we can actually truncate it. Okay. So that is that is how actually we are using Gauss-Seidel. But the problem here is we have to make sure all the bus voltages are truncated. All the bus voltages are needs to be converged. This is the most important part, because if one or two bus converge and others does not converge, then we cannot actually stop the Gauss-Seidel. So that's why it takes many number of iterations. It takes many number of iterations. So similar to the Gauss-Seidel, also we can also use some step known as a Gauss-Jordan iteration. Actually, both are actually similar only. So it depends. The main difference between Gauss-Seidel and Gauss-Jordan is the iteration, like updation. So how are we actually updating the the next value in the next iteration, or actually we can just check what is the basic difference between Gauss-Jordan and Gauss-Seidel. So here for finding V3, if we use the the value of the voltage what we get here, that will actually go to Gauss-Seidel, and if you use the previous value of V2 itself, so that will go to Gauss-Jordan iteration. Okay, like both are actually very similar only. So one of the important drawback of our Gauss Seidel method is that it requires many number of iterations. That is basically it is time consuming. Right. It is very time consuming because it requires a lot of many number of iterations. So we have to develop some other method by which actually this can be avoided. Okay. So that method is basically known as Totem Props. So if you think about the Newton-Raphson method, actually I think you have studied about Newton-Raphson method for finding roots of a transcendental equation, right? So like this, if there is something x minus sin x plus b cos x equal to 0. So how will you find the value of x? This is not a linear equation, right? Because this contains some sin x and cos x. These trigonometric terms are actually present here. So how will we find the roots of this equation? So like these equations are basically known as the transcendental equations, right? So for finding roots of this equation, we can either use something known as a bisection method, right? So in bisection method, what we choose some, we assume that the roots are actually between some numbers. Then we will actually take the half. Then I think you understood this thing. So that is basically known as the bisection method. So, but bisection method is actually computationally expensive, right? You study the algorithm part, like it's computationally very expensive. So due to that, we actually use something known as a Newton-Raphson method. Right? That is basically a derivative based method. That is, it requires only very less number of iterations. Right. That is the important of Newton-Raphson. So I think you have studied all these things in your engineering mathematics. So similarly here also we actually use the something known as a Newton-Raphson, right? So the important thing is that here the number of iterations are very small. Okay. So we can actually look at something. Assume that f1 is a function of x1 comma x2 is equal to some constant k1. Okay, right. Now similarly there is another one f2 of like x1 comma x2. This is equal to some k2. So this may not be some linear equation, okay, because this can be something like a transcendental equation. So we have to find what is x1 and x2 which satisfies this particular condition. That is like very like we use this kind of things in our daily life, like most of the equations in power system or most of the things actually coming in engineering, so it may not be linear, right? So that there are going to be non-linear equations and transcendental equations, so everything can come. Okay. So in order to solve this, what we write is we write here k1 equal to function of x1 comma x2, right? And we actually write like f1 of x1 0 plus delta x1 0, comma x2 0 plus delta x2. Right. So basically this is that there are some values of x1 and x2 that will be actually gives this k1, right? So what we are doing is we are taking some initial guess x1 0, and we know that this may not be the exact solution, right? Because we don't know what is the exact solution. So but if we add something to this thing, that will be the exact solution, right? Because there will be some error will be there. Okay, so that is basically delta x1 0 and delta x2 0. Okay. So similarly, if you write k2, we can write that is basically f2 of x1 comma x2, right? That is f2 of x1 0 plus delta x1 0, comma x2 0 plus delta x2, right? So this is basically thing. So here actually this x10 plus delta x10 is the exact solution, right? Right. And x20 delta x10 is the exact solution. So, but we don't know what is exact solution. We know that it is some x10 plus some delta x into x0, right? x10, right? So, like now, what we are going to is we are actually taking the Taylor series expansion of this particular. Okay. That means K1 can be represented as f1 of x10 comma x20 plus delta x10 into dou f1 by dou x10 plus delta x20 into dou f1 by dou x2. Right. Like this. So this is basically the Taylor series expansion of this one. So like at this particular point x10 we have to multiply with this one. There will be higher order terms also. So what is basically K2? K2 will be f2 of x10 comma x20 plus delta x10 into dou f1 by dou f1 by dou x1 0 plus x20 into this dou f2. Dou f2 by dou x2 at x20, right? Was higher. So we are neglecting all the higher order terms. Okay. Now we can write K1 minus f1 of x10 comma x2. Here also K2 minus f1 of x10 comma x2. Now check here. That will be equal to, we can write dou f1 by dou x1, dou f1 by dou x2, dou f2 by dou x1 into dou f2 by dou x into delta x10 delta x2. Right. Now check here. So what is this? This is basically we assume some thing x10 and x20, right? And that is actually we are taking the minus of this with this one. So that is basically this is the residue, right? Right. And this is the initial guess actually what we are actually putting here. So this is the residue. So that means we have to minimize this one, right? So if this is actually 0, assume that these are actually 0. So that means this x1 is the exact solution, right? So if we minimize this one, or in another way we can say if we minimize delta x nearly 0, that means x10 is the exact solution, right? So we have to minimize this particular function. So we know that this one. So from here, if you make it 0, then actually we can find the solution. That is how it is actually working. Okay. Now we know this one, right? Because we know K1, we know the initial guess, right? And this can be actually expanded. So from here, what we are actually finding is this one, delta x10 and delta x20, right? We can actually find this because all these are actually known. This is also known. This is the unknown. So basically, we can actually find delta x10 every delta x10 and delta x20. So from here actually we can find this, right? Now we will update it. So x11 right here. So x11 will be equal to x10 plus delta x1, right? Similarly, x21 will be equal to x10, sorry, x20 plus delta x2. The most important thing in here is this is actually only one-time computation, right? This thing can be computed only once, right? Because This is actually this will be remains constant everywhere, right? So this function needs to be computed only once. Right. Then we have to just substitute the values here. That's all. Right. So that function we don't calculate again and again and again. Right. That is the important advantage. So similarly, actually, we can have the iteration time. So you can just write down this and we can go forward. So now we can actually look at our problem, okay, our dot flow studies. So how can we use Newton Raphson method in dot flow studies? Okay. We are taking some base voltage Vk, that is basically mod Vk into angle delta K. Then Vn equal to mod Vn angle delta N and Ykn equal to mod Ykn angle some theta K, right, like this. Now we can write Pk minus Jq, right, because this is V2 into like Vk into Ik star, sorry, Vk star into Ik. It is basically n equal to 1 to n mod of Vk, Vn, Yk, sorry, Ykn into angle theta Kn plus delta n minus delta, right. Now we can actually find Pk and Qk. Basically Pk will be equal to, take the real part of this one, right? So sigma n equal to 1 to n mod Vk, Vn, Ykn cos of theta Kn plus delta n, right? Because here the delta K is negative because, like, we are taking the difference between the things. Okay, that's why actually this is continuous negative. Because I2 will have a negative. And Qk will be minus of sigma n equal to 1 to n mod Vk, Vn, Ykn sin of theta Kn plus delta n, delta. Right. So this is the condition. Now we can use the this one. Now we will be actually taking our functions as P and Q. Okay. So we will actually make delta Pk basically equal to Pk specified minus Pk calculated. Similarly, delta Qk will be equal to Qk specified minus Qk calculated. Right. So once this Pk and Qk are actually, this is in some range of epsilon, then we can stop the iteration. Right. Now we can write these are the equations. Okay. P and Q. What are the variables? V and delta. Okay. So this is the two functions what I have written there. Okay. Now we can write the it in the ghost, or sorry, in the Newton-Raphson form. That is delta P2. Right, just take two bases. Okay, that will be more easy. Delta Q2, delta Q3. Okay. So here, this P is a function of delta and V, right? That's what I have written there. P is a function of delta and V. That is dou P2 by dou delta 2, then dou P2 by dou delta 3, then dou P2 divided by mod V2, and dou P2 divided by dou V3, right? Similarly, dou P3 divided by dou delta 2, then dou P3 divided by dou delta 3, dou P3 divided by dou mod V2, dou P3 divided by dou mod V3. So this part is done. Now we can answer Q. So that is dou Q2 divided by dou delta 2, dou Q2 divided by dou delta 3, then dou Q2 divided by mod V2, dou Q2 divided by V3. Similarly, dou Q3 divided by dou delta 2, dou Q3 divided by dou delta 3, then dou Q3 divided by dou V2, then dou Q3 divided by dou V. So this multiplied by what will be dou delta 2, dou delta 3, dou V2, dou V. This will be our equation, right? So now in the given question, we will get some value of P. We can start with some value of P. P is specified, and we can start with some value of voltage. So from there, we can find the delta P, right? Here, this we can fill. Then this you can directly find from the equation of P and Q, right? Because P and Q depending upon voltage and delta, right? So from here, actually, you can find the derivative of all the like dou P with respect to delta 2, delta 3, and everything we can find. Okay. So this is basically like we can find that. Okay. So then we can find, so in the first iteration we can find delta 2, right? Then delta 3, delta V2, and delta. Take the inverse of this one and multiply this one. Okay. So we can find this one, then we can update it using this one. Then again we can find this. Then check the change is very, very small. Then like this we can actually go and update and everything. Okay. So this is actually by which actually we are doing the Newton-Raphson. So it is computationally complex because we have to find out of different derivative and everything here. It is computationally complex, but it got only less number of iterations. So with this very less number of iterations, actually we can solve this one. So that is the the most important thing with the Newton-Raphson. Okay. So by this actually we can and there are some more thing is there. So the main problem with this matrix is that this is almost a full matrix, right? It is very difficult to take the inverse of this one. So what we normally do is we'll actually consider as something known as a decoupled analysis. So in decoupled analysis, what we normally take is that we already know that from the electrical machine perspective, this Q and V is actually related and P and delta is related, right? So because P equal to EV by X into sine delta, and Q is actually related to V, right? So dependency is more there. So we are actually neglecting this part, total part, and this. So the interdependency of P with respect to V and Q with respect to delta is actually we are not considering, right? So what we'll get is we'll get something like this. I will write the next page. So if we actually consider the past decoupled delta P, P1, delta P2, sorry, P2, P3, delta Q2, delta Q3 will be equal to some matrix here. I can write dou P by dou delta, then it will be 0, 0, and dou Q by right into delta B, sorry, delta delta 1, delta 2, delta delta 3, delta B2, and delta B, right, like this. Now the thing is that this is basically decoupled, right? So this is basically this into this, right? And here also this is this into this. That means Q depending only on V and P depending only on delta. So this can be independently solved, and very fast we can actually get the convergence. Okay, there will be small error, but like this is computationally very simple. This is known as the decoupled load flow studies, and some places actually will be using this also. Okay. You can actually check this in some of the textbooks. They will be actually in most of the textbooks. I don't know, but they might give in some of the textbooks. Okay. So I hope you understood things, and you can write all these things, and then you can start the next important portion of the power system analysis, that is economic load. You can write this thing, and then we'll go to the economic load. Okay. So So what is basically economic load dispatch? From the name itself, I think we can actually get what is the basic meaning of economic load dispatch. So the load dispatch should be economic. That's all. That is, there should be, the plan should be efficient, to provide load economic. Right. So this is basically the economic load dispatch. Okay. So like so the power generation, or the power, actually the what to say, the power system should should run at maximum efficiency, right? Then only actually we can say it is something like an economic load dispatch, right? So now just think about an electrical actually generating station. Okay, so there is something like an electrical system, and there is something like a mechanical system, right? These are actually coupled, and this generate and this will be load. So, so the in the earlier days, what we are they're actually did their best in what to say, best in increasing the efficiency of boilers, turbines, and generators. Right. So there are many methods by which we can actually increase the efficiency of boilers, turbines, and generators. Now the thing is that how we are actually giving the load in an economic way. Okay, because here the mechanical side and this part of generating side, everything is we can actually have different methods by which we can increase the efficiency. So here, we are actually we can consider increasing the efficiency by providing the load. I'll just say one example. There is one generation station here, and there is another generation station here. Okay, there is some load here. This is the place where. Okay. So this is one transmission line, and this is another one. Okay. So this is the load. So this generation station is like you can say almost like 300 kilometers. Assume here this is actually 100 kilometers, right? But they made in such a way this is the most efficient, right? This is actually running at the maximum efficiency. So the load demand here, you can say the load demand here is almost like 500 megawatt. Okay. So this can like this rating is you can say something like 400 megawatt, and here it is something like 300 megawatt. So now the question will be like this. So should this provide this 400 and this provide 100, right? Because if it provide 400 megawatt, there will be huge loss actually happening here, right? Because the distance is more here, but it is having the good efficiency category. So that will be one. So another question will be like, should this provide 200 and this also provide 200, right? So or this provide 300, 100, or this provide 300 maximum. Right? So these kind of questions will come, which one should provide the the thing. Okay. Or in another way, we can say like this: there is like I will say this. So this is basically known as the economic load dispatch. So we have to consider the losses, we have to consider what is the efficiency, and we have to consider something known as the incremental fuel cost. Okay, like that I will be explaining later. So all these things you have to take and you have to consider, and then only we can decide what is the how much load this has to give and how much load this has to give. Okay. So and what if this 500 is increased to 700 or 600? Then should this give 400 and this give 200 or 300, right? So like this, we have to take some decisions in actually dispatching the load, right? That is basically the economic load dispatch. That is the basic idea of economic load dispatch. So I'll give you one more example. So assume that this is a substation, or it's a generating station. This has got 5 or 6 generators. This is generator 1, generator 2, generator 3, generator 4, and generator. Right. So this has to provide some loads. So this combinedly it will provide some 1500 kilo or mega. Just some random numbers. So in order to produce some amount of megawatt here, there will be some amount of cost for this particular generator. So the cost will be for this different for this particular generator. Cost will be different for this one. So we can say cost 1, cost 2, cost 3, cost 4, and cost 5. Okay. Like for producing 1 megawatt of power, like we can say like this: for producing 1 megawatt of power, this this may require like 10 rupee. Yes. For producing 1 megawatt here, it may require some like 12 rupee. So here it may take something like 20 rupees. Here it may take something like 5 rupees for producing 1 megawatt of power. Here also it will take 1 rupee, assuming like this. So that means what is the most effective way of distributing the load? Such that the cost is minimized, right? So that is, we have to minimize the cost function. We have to minimize the cost function, right? This is the most important part in an economic load. So which generator should produce what much of power, right? So if you look in the in the practical scenario, there will be something known as a load dispatch center, right? So every places there is something known as a load dispatch center is there. So it will decide which generator has to run at what, this one, right? What like every generator will have some cost is there. So so it will run a computer program such a way that the result of the program will be this generator has to give this much of load, this generator has to give this much of load, like that. Okay. So that is basically known as a load dispatch center. So like which generator has to produce what amount of current and what amount of power, and where actually this this should be connected, like that. So this is the things what a load dispatch center will do. So almost all the states and the national wide also there is actually load dispatch center is there. Okay. So that is basically known as the economic load dispatch. Okay. So the aim of an economic load dispatch is what is the most effective way of sharing the load between the generators and the substation, or what is the most effective way of sharing the load between different generation stations. Okay, so this will be actually two things. First is sharing. Okay, I will just say something. Some places records like something like 1500 megawatt. Okay, this much of power some place. Actually, there are two generating stations there. So one generating station has a capacity of 800 megawatt. Another has a capacity of 1000. So this 800 megawatt is actually coming from some 5 generators. Okay, something like we can say something like 200, 200, 200, 100. So this 1000 is actually coming from some another 5 generators. Okay, so something like 500, sorry, 300, 200, then 200, then 100, 100. Okay. So like 50, 50, 4, 7, 9. So this is also 2. So like, so the first question is how this 1500 should share between these two generating stations. This generating station 1, this generating station 2. Right. So how this 1500, like we can share this way 700 and 900, right? Sorry, 800. So assume that this is the most economic way of actually sharing the load. Now the second part of this problem will be how this 700 is shared between these 5. Okay, so should it be like this one way of doing this is we can directly shut down this one, right? So this 100 thing can be shut down, and all others are actually run into their maximum capability. So we'll get 700, right? So but the problem is that if you look at the performance curve of most of the electrical machines, like you can actually just go and check what is the synchronous machine performance curve. The efficiency is maximum at some load which is not the rated load, right? Which is less than the rated load. We will get the maximum efficiency at this particular. That means it is not so judicious to shut down one and use all others to their maximum, because that will be actually less effective, efficiency will be less here. So we have to actually distribute the load between these 5 such a way that almost all the generators are near to their maximum. Near to their maximum. So similarly, here this 800 watts will be distributed between these 5. So what is the way? Okay. So in earlier where there was no computer, all this kind of algorithm was not there. So what they will do is they will choose which is having the maximum efficiency, right? So the efficiency of this is like 85, 83, 82. So they will first load this to full. Then load the next efficient one. Then load the next efficient one. Then load the next efficient. So we will get 700. So they will stop there. But later we got understood that that is not enough, right? That is not the exact way of actually doing it. So we can actually divide the load into, because this will be permanently shut down that time, right? So we can share the load in here also, such that almost all the machines will be actually working in a near to this maximum efficiency. So that is another way of actually looking at the same problem. Okay. So I hope you understood this thing. Okay, so you can actually write it. So in each generator, will have something, will have a property called incremental cost, fuel cost, right? So assume that this generator is actually working at half of the load. Then assume that it's 50, that is half. Then it has to go to 50 to 51, right? So how much energy or how much fuel is required from reaching from 50 to 51, right? So assume that look at some some 10,000 liters or something for that one. So we need to, so a cost of 1 liter is basically something like 50 rupees or 60 rupees. Then multiply with this, we will get the incremental cost for. So the basic problem is that it may not be exactly linear everywhere. That means 50 to 51, if it is 10,000 liters, then 51 to 52 may not be exactly 10,000, right? Because it can be less than 10,000 or greater than 10,000. So similar for, that means for each for each power output, there is something known as the incremental cost, right? Incremental fuel, right? So we write like dFn by dPn. Okay, this is F is the fuel cost. Okay, and P is the power. That will be, we can say, it is almost a linear one. So in most of the questions, it will be actually, we'll be assume it to be linear. We will take the slope of that particular curve. Okay, so if I consider this like this, will be incremental fuel cost, and this is the power output. If the curve is actually like this, something like this, then we will actually assume a nearest straight line. So we'll assume this one, like, so we can write, for example, we can write something like 0.02 plus 8 point, something like this will be the y-intercept. So it will be actually touching here at particular y-intercept. So something like this will be actually the incremental fuel cost. So the incremental fuel cost for a unit given power output is the limit of the ratio of the increase in cost of the fuel input in dollars per hour to the corresponding increase in power output in megawatts as the increase in power output approaches zero. Okay, like that is basically this one. So at this particular point, what is the slope? At this particular point, what is the slope? This is basically the incremental fuel, right? So all the slope at this particular. Okay. So like this, actually, we can find the incremental fuel cost for all the generators, right? That is the total fuel cost FT will be fuel cost for F1, F2, F3, etc. up to Fk. That is basically the cost for all the fuel, right? So in order to generate some amount of power, we have to take the cost for all the generators, right? That is sigma n equal to 1 to n f. And each of the things produces some power. So total power will be P1 plus P2 plus P3, etc. up to Pk, right? So that is sigma n equal to 1 to k Pk, right? So Ft is the total fuel cost and Pr is the total power, right? So I hope you understood, right? So we can write like this now, because now we can write dft, change in fuel cost, will be dou ft by dou p1 into dp1 plus dou ft by dou p2 into dp2, etc. up to dou ft by dou pk into dp, right? Because this ft is a function of f1, f2, f3, right? But f1, f2, f3 is a function of p1, p2, p3, because this is the fuel cost. So the fuel cost, incremental fuel cost, will be a function of the power generated. So that's why we actually have to consider the partial derivative. Okay. So but we know that the change in power dp1 plus dp2 plus dp3, etc. up to dpn will be 0, right? Because assume that there are 10 generators are there, it is sharing equally, right? Then we know that after calculating the economic load dispatch, we increased one of the things to something. So in order to make all the power, some of the power constant, we have to simultaneously decrease someone also, right? So that the total change will be actually 0, right? That is basic. Okay. So I hope you understand, right? So if you just subtract this one, and we have, if you multiply some constant, multiplying with a constant lambda and subtracting, so we can write like this. So it will be like this. I'll write the next page. That is dou ft by dou p1 minus lambda into dp1 plus dou ft divided by dou p2 minus lambda into dp2, etc. up to dou ft by dou pk minus lambda into dpk will be equal to 0. So the easiest solution will be everything should be equal to 0, right? That is dou f1 by dou p1 is equal to lambda dou f2 divided by dou p2 is like this. Dou f k by dou pk will be equal to some constant lambda. This lambda is known as a Lagrange multiplier, right? So if this condition is satisfied and p1 plus p2 plus p3, etc. up to pn equal to pr, then this will give the most economic load dispatch. So this is the condition we have to actually look at. Okay. So I hope you understand the thing. So by this actually we'll be ending the class. In the next class, I will give you some basic examples for how to do the how to do this. So this is there are another ways by which we can derive this. This is the most simplest way. So I have derived this way. So it will be basically it will be very easy. Okay. So the next class I will give you some examples how to find this electromagnetic load dispatch in some numerical things are there. So you will get understand how exactly. Then we will look at the how the losses affect. So we have to look at the penalties, right? Because the losses depending upon the distance. If the maximum efficient generator is way long back, distance is so large, so that we actually cannot consider that as it's the most economic way, right? Because their losses are very, very high, right? Because if you consider that way. So that means we have to include the losses term also in this one. Okay, here we are not considering the losses. So the next like tomorrow, we will be actually looking at how to include the. Okay. So I hope you understood this one. It is very simple, and we can look at the things in the next class. Thank you.